Hi, and welcome to the second video of my concrete sustainability series. For those of you who are viewing this video first, my name is Nikola Tosic, and I am a teaching assistant and PhD student at the University of Belgrade's Faculty of Civil Engineering in Serbia. Last week we talked about the problems that the production of concrete poses, mainly in terms of its environmental impact. We saw that natural resource depletion, large CO2 emissions, and waste generation are the main issues. If you want to see that video again, you can find the link in the description. Today, I will try to present potential solutions to these problems, ones that are being investigated globally, that seem to be most promising and closest to full implementation. Let's get started. So we saw that the problems with concrete production were resource depletion, waste generation, and CO2 emissions. And we also saw that the main components of concrete are water, aggregates, and cement. The question is then, with what can we replace each of these components to make concrete more sustainable? I will focus in this video on aggregates and cement, since their use is a much greater environmental burden than water consumption. One thing we can do, and this has been studied for several decades, is to recycle construction and demolition waste, to make new aggregates and use them instead of the natural ones. This approach would deal with two problems simultaneously. It would reduce the depletion of natural resources and reduce the amount of waste being landfilled. So is it possible? In fact, yes, construction and demolition waste can be recycled. We'll see later in the video how it can be done and what are the issues it raises. Another option we have is to reduce the amount of cement we use. By doing this, we would also reduce natural resource depletion and, more importantly, reduce the CO2 emissions from the production of cement. Cement can be replaced by so-called supplementary cementitious materials. The most widespread of these are blast furnace slag, which is a byproduct of steel production, and fly ash, which is a byproduct of coal combustion in thermal power plants. They can be used to either replace a certain percentage of cement, in which case they are truly supplementary materials, or they can be used in concrete composites produced completely without cement, in which case these materials are activated with alkaline solutions to produce inorganic aluminosilicate polymers, sometimes called geopolymers or alkali activated concretes. Now let's get back to the first solution, recycling of waste concrete. After a concrete structure is deemed to have completed its lifespan, due to whatever reason, it is demolished. Even before it is actually demolished, the recycling must begin by stripping it of any unnecessary materials such as wood, glass, gypsum, masonry, so that only concrete remains. In the next phase, the structure is crushed into large and small pieces by hydraulic crushers and hammers. The recycling of this waste usually involves a two-stage crushing and sieving process and the removal of any remaining impurities. The process is carried out in mobile or stationary facilities, using so-called jaw crushers and impact crushers, depending on the fineness of the waste material and the desired quality of the product. You can see examples of recycling facilities on your screens. The aggregates produced in this process are called recycled concrete aggregates, or RCA, and when they are used to produce new concrete, that concrete is called recycled aggregate concrete, or RAC. Since concrete consists of natural aggregates bound by hardened cement paste, after recycling, a certain amount of this residual cement paste is left bound to the aggregates. This means that the final product of recycling, recycled concrete aggregates, are a two-phase material containing natural aggregates and cement paste. The presence of this residual cement paste causes a certain deterioration of recycled concrete aggregate properties compared with natural aggregates, such as higher porosity, higher water absorption, and potential contamination with chemicals if the old structure was in such an environment. Because of this, recycled concrete aggregates are still mainly considered to be inferior compared with natural aggregates, and are relegated to use in applications such as road subbase and non-structural elements. However, the positive effects of concrete waste recycling can be fully utilized only if recycled concrete aggregates find their use in all types of concrete, especially structural concrete. But currently, only 1% of aggregates used worldwide in structural concrete production are recycled concrete aggregates. So what are the reasons for this situation? Unfortunately, only certain countries are dedicated to construction and demolition waste recycling. These are mostly developed countries, which either face a shortage of natural resources or have little available space for waste landfilling. So Japan recycles an astonishing 98% of its construction and demolition waste, the Netherlands 90% and Denmark 80%, to name just a few. On the other side, countries with vast deposits of natural aggregates or with large territories for landfilling tend to recycle less. The USA about 20 to 30% of its construction and demolition waste, and Italy about 9%. A stereotypical view also exists that a recycled product must be inferior to the original, and this leads to a lack of trust in using recycled concrete aggregates. This is just further enforced by the lack of regulations for its use and certain legitimate uncertainties regarding the technology for producing recycled aggregate concrete. Fortunately, all of this is being studied and investigated, and things are improving. The technology for producing both recycled concrete aggregates and recycled aggregate concrete exists and can be implemented. It must, however, be made cheaper, and the use of recycled products must clearly be presented as a benefit for both society and the environment. Economic measures, such as increasing waste landfill taxes, introducing taxes on natural aggregates, and subsidizing the recycling industry are all potential measures. Knowledge transfer must be intensified from the scientific community towards industry, and the dialogue within the whole society concerning environmental problems and potential solutions must be maintained. Hopefully all of this will bring us closer to structures like this one, the Waldspirale in Darmstadt, Germany, designed by the famous architect Friedensreich Hundertwasser and built back in 1998. For its construction, around 12,000 cubic meters of recycled aggregate concrete was used for all indoor structural elements. Okay, now let's move on to the second option we mentioned, the reduction of cement use through so-called supplementary cementitious materials. Here I want to focus on the most abundant one, fly ash, the byproduct of coal combustion in thermal power plants. The World Bank data shows that in 2013, 41.3% of total electricity produced came from coal-burning thermal power plants. After coal combustion, a fine micron-sized powder remains, called fly ash, and in huge quantities. The US produces roughly 130 million tons of fly ash each year, China and India 300 million tons. In Serbia alone, just one of our 6 power plants produces 100 tons of fly ash every hour, and 24 hours a day, 365 days a year. In fact, in Serbia, about 200 million tons of fly ash are currently deposited at a surface area of 1,500 hectares. Fly ash, as well as a number of other industrial byproducts, consists mainly of silicon and aluminum oxides, and has so-called pozzolanic properties, which means it reacts with cement hydration products and enforces the paste matrix, contributing significantly to the properties of the final material. Having this in mind, it is reasonable to assume that the replacement of a certain amount of cement by fly ash will not have negative effects on concrete. Such concretes in which more than 30% of cement is replaced by fly ash are called high-volume fly ash concretes. Because the pozzolanic reaction is slower than cement hydration, high-volume fly ash concrete has a slower strength development than ordinary cement concrete, which has to be taken into account. The benefits of using fly ash include better workability due to a finer packing density of particles and improvement of certain durability-related and long-term properties such as shrinkage. There is also the possibility of completely replacing cement with fly ash, but then it has to be alkali activated with chemicals such as sodium hydroxide and water glass. These alkali activated concretes can have some properties even superior to the traditional cement concrete, but the use of chemicals makes the ready-mixed production of these concretes complicated. Perhaps they are better suited for the production of prefabricated elements. Encouragingly, more and more companies are being set up around the world, dedicated to the production of alkali-activated concrete or high-volume fly ash concrete, or concretes with other types of industrial byproducts such as slag. Now that we've covered some of the options of making concrete more sustainable, I hope you have a better understanding of the underlying issues and ways we can deal with them. These topics are very wide, and these videos are far from an exhaustive source for studying them, so I put some useful links in the description for investigating further. I hope to see you next week when I'll present the work being done in Belgrade by our concrete structures research team and how it fits into the bigger picture that we've discussed up to now.